Thank you and welcome to the last session of the day. I don't know about you, but I'm having a really good J-Point. This is my first time at J-Point. It's actually my first time in Moscow. I'm having a really good time and really enjoying it. But it's getting late now. It's 6:30 in the evening. I know I'm getting tired, and I guess you guys are too. We've had a really good conference. There's been lots of technical detail as we've gone through the day. My brain has just got fuller and fuller and fuller as the day has gone on. And that's how it should be, of course. But here I go again, late in the evening, starting yet another technical presentation. So maybe I'd suggest that rather than digging into the absolute low-level technical details, that I'd like your takeaway to be more to get a feel for the API, how it's used, how it operates, and the shape of it, so that the next time that you find yourself needing to do HTTP requests, that you at least consider using this client as opposed to a different third-party client that's configured. So just a few words about myself. My name is Crys Hegarty. I'm from Dublin, Ireland. I studied computer science in Dublin City University, and I've been working on Java platforms since I joined Sun Microsystems in the year 2000. I now work for Oracle, and I continue to work on the Java platform. Ireland is a small country on the other side of Europe with a very small population of less than 5 million people. That's less than half the size of the population of Moscow City. We're well known for some of our exports. Probably the best known one is our dark, dry stout, which is Guinness. It's been brewed in St. James's Gate for over 250 years. And anywhere you find Irish people around the world, you will find them celebrating on the 17th of March. This is St. Patrick's Day. It's a religious and cultural festival that we have. And this is a picture, Wikipedia assures me, of a St. Patrick's Day parade in Moscow. Quite often, we celebrate St. Patrick's Day with quite a number of pints of Guinness, so they go well together. So if you didn't believe me when I said I work for Oracle, you probably will believe me now. So if you see any technical presentation by Oracle, you will almost always find this slide. And this is the standard Oracle Safe Harbor statement, and it's warning you, the audience, to basically not believe a word that I say. And quite often this is applicable because the group that I work in is responsible for developing and maintaining new features in the Java platform itself, the core libraries and networking libraries. And them new features often get discussed and talked about at conferences like these while they're still being developed. And of course, while any piece of software is being developed and before it becomes standard, it's subject to change. So that's what this slide is all about. But in this case, everything that I'm going to show today is already in Java 11. And Java 11 shipped in September last year. And as you know, we take compatibility of the Java platform extremely seriously. So everything that I show here today is already subject and under the rules of JCP. Okay, so this is the general outline that we're going to follow. I'd like to talk a little bit first about the development process and some of the deliverables along the way. And the reason I think this is important is because we used a new development process for the HTTP client. We'll then move on to the API itself. We'll have a look at the top-level types, how to use it. And finally then, I'd like to dig a little bit deeper into the use of Reactive Streams in the client and its interoperability points with other Reactive Streams implementations like RxJava, Akka, or Reactor, to name but a few. What I will not be talking about today is performance. And the reason I won't be talking about it is because there are already a number of good talks about performance. And Sergey Kuksenko did a talk here in 2017, and it's very, very good. So if you're interested in performance, I go and recommend that. Sergey also has some other talks that you can find online. So when we're working on any project, we are asked a number of questions, among them the ones like these. So why are we working on this? Why does the Java platform need a new HTTP client now? And what are the benefits that you can get as an application developer from the HTTP client? And also, what benefits do we get as library maintainers of the OpenJDK? Because there's benefits on both sides here. So why are we doing this now? Well, prior to this work, the only supported way to do HTTP exchanges in the Java platform is through the HttpURLConnection API. Of course, there are many third-party libraries, but we feel HTTP is a significant enough protocol, the whole web runs on top of it, that the Java platform should support HTTP out of the box. And of course, recently, there's been a new standard. HTTP2 has been published as an RFC, and we want to make sure that we have support in the platform. Enhancements in the JDK are done through JDK enhancements proposals, JEPs. And JEP 110 is one of the first public documents that we have on the new HTTP client. And it's useful to look at the motivation in this JEP. There's a number of points discussing the URL connection API, which is the prior API for doing HTTP exchanges. That API is agnostic of protocol, and it supports multiple protocols. In fact, URL connection was added in JDK 1.0 in 1996. And if we look at the HTTP timeline, we can see that the RFC for HTTP 1.0 was published in 1996, so the same time as JDK 1.0. The HTTP 1.1 RFC was published in 1999. And then more recently, we've had HTTP2 in 2015. The URL connection API, or more specifically, the HTTP protocol handler, has had countless bug fixes over the more than 2 decades, has had numerous enhancements added to it, and it's really reached a level of complexity that just from being around for more than 20 years, it's very, very difficult to make changes in it, and especially trying to implement something like HTTP2 would have been very, very difficult. The URL connection is also based on Java I/O streams, which are inherently blocking. So this may not have been a problem back in 1996, but it certainly is today. Threads are a valuable and costly resource, and we don't want to unnecessarily tie them up waiting on data to be received from the network. Looking again at the HTTP timeline, we can see that HTTP2 RFC was published in May 2015. The application semantics of HTTP are mainly the same as that. HTTP2 are mainly the same as that of 1.1. The core concepts, the requests, responses are mainly the same, but HTTP2 modifies how data is formatted and transported. HTTP2 also does bring some new concepts that would have been very difficult to model in the URL connection API. One of which is server push, which we'll take a look at later. And the HTTP2 implementation is very, very different from that of 1.1. So all of these things combined led us to the conclusion that we'd be better adding a new HTTP client rather than trying to retrofit some of this stuff into the existing URL connection API. Well, defining a new HTTP client API for the Java SE platform is not easy, especially if we expect it to be around for the next 20 years. So JEP 110 was created in May 2014, which is almost exactly a year before the HTTP2 RFC was published. And work actually began well before this date, in fact, around the Java 7 timeframe, and it was done in the java.net site, which is still available somewhere in the archives. So this project has been running for a number of years and has been worked on by several engineers. JEP 110 was integrated into JDK 9, and JDK 9 shipped in September 2017. As you all know, Java 9 brought a large language change in the form of the module system. And the Java runtime image is now comprised of a set of modules. Alongside the module system, we added a new concept of incubating features. And the HTTP client was added in JDK 9 as an incubating feature. A new incubator module named JDK Incubator HTTP client was added, and that module exports a single package that contains the complete API. So JEP 11 describes what incubating features are, their purpose, and their delivery mechanism through incubator modules. But simply put, incubator modules are a means of putting non-final APIs in the hands of developers, while the API progresses towards finalization or removal in a future release. So this is a very powerful thing for us in the OpenJDK, to be able to deliver something as early as possible, and also to be able to incorporate feedback after we've delivered it, to accept feedback from you guys and to be able to incorporate it in a way before the API gets standardized. This is not preview features, which are different. Expression switch is a preview feature in Java 12, and preview features are more focused on language and VM stuff. Incubating features are more relevant to bodies of code with large API surfaces. So that's what we did in JDK 9. And then in JDK 10, we refreshed the implementation. We completely overhauled it. We improved reliability and robustness. And we took the opportunity to incorporate feedback that we received on the Incubating 9 version. And we did receive some feedback, and it was very useful. Then for Java 11, we filed a new JEP 321, and we standardized the client. So when a standard module and package has to be in the java.star namespace, that's what it means to be in the Java SE specification. The incubating code was completely removed, so any code that was depending on the incubating code will need to be rewritten. At the very minimum, it will have to have its import statements updated to reflect the new module, the new package name. If you've got a module info that requires the incubating module explicitly, well then its require statement would have to be updated to reflect the new module name. So why would you want to use the new HTTP client? Well, again, JEPs are very useful documents. They're live documents, and it can be useful to go back and to look at the JEP. And JEP 110 is a number of goals. And the most significant of these are, the most significant, I guess, is we have support for HTTP 2. We also provide support for both synchronous and asynchronous modes of operation. The API is more modern, at least more modern than URLConnection, which was designed before Lambda and generics. And we took the opportunity to use more modern platform types like completable future and the Reactive Streams interfaces. And there's also support for a low-level WebSocket client. Briefly looking at some of the high-level benefits of HTTP 2. I only have one slide on this. You could have a whole session on this. But as I said earlier, the application semantics of HTTP 2 are very similar to that of HTTP 1.1. But the two protocols are very, very different in how they operate. For example, there's only a single connection between the client and server, and multiple requests can be sent on this connection in parallel. So this helps reduce the overhead of setting up new connections, especially when them connections are using TLS. And it helps reduce the overhead on servers. HTTP 2 does bring a new concept of server push. This is where a server can send a client resources without the client having requested them resources. And the server knows how to do this based on the client's initial request. The HTTP client API supports server push directly in the API, and you can get access to the pushes from the server. HTTP 2 also uses a binary, on-wire format, and HPAC compression, so it's much more efficient than HTTP 1.1. The HTTP client also supports both HTTP 1.1 and HTTP 2, but in all cases it prefers HTTP 2. So if you've got a clear, non-secure connection, the client tries to upgrade that connection to use HTTP 2. If you've got a secure connection, the client uses the TLS Alpine extension to negotiate H2 with the server. And in all cases, if the server supports HTTP 2, well then that's what would be used. And if not, the client would automatically fall back to using HTTP 1.1. JDK 11 brought support for TLS 1.3, and the client, in all cases, tries to negotiate TLS 1.3 with the server. As I mentioned, one of our goals is to provide a more modern API with both synchronous and asynchronous modes of operation. The asynchronous API is supported through JavaUtil concurrent completable future. We followed the familiar builder style pattern, and all the types are immutable. Processing of request and response data is done through, supported through Reactive Streams, and the Java platform supports the Reactive Streams interface through JavaUtil concurrent flow. There's a publisher and subscriber. Okay, moving on to the API itself. So the top level type is HTTP client, and you can use this to send requests and get responses as you would expect. A client is built from its builder, and the builder can be used to set per client state. For example, whether you prefer HTTP1 or HTTP2, whether to follow redirects or not, if you need a proxy, an authenticator if the request requires authentication, and a connect timeout if the client needs to open a new connection to send a request. The client shares resources as you would expect, for example, like a connection pool, so subsequent requests sent to the same destination can reuse the connection. Here is an example of a code to build a new client. In this case, you get an instance of the builder from the new builder factory method. The version is set to be HTTP2, which is the default anyway. Redirect policy is set to always redirect, unless you're being redirected from the more secure HTTPS to the less secure HTTP. Proxy support is provided through the dynamic proxy selector API that's been in the Java platform since I think 1.4. It's a relatively rich API that allows you to do dynamic proxy selection based on the URI that you're connecting to. In this case, or in many cases as well, you just want to configure a static proxy. So the proxy selector of method allows you to create a proxy selector that will always return you a proxy of the given socket address. The authenticator in this case has been set to the system-wide authenticator. So if a request requires authentication, the user credentials will be pulled from the system-wide authenticator. And then a connect timeout duration of 20 seconds is set. So if a connection cannot be established within 20 seconds, it will fail with a suitable error. And once built, the HTTP client is immutable and it can be used to send multiple requests. Okay, now you've got a client, you need a request. And a request follows the same pattern. It can be built from a builder, and you use the builder to set the per request state. You've got everything there that you would expect: a request URI, request method, a body if there is one, some headers, and then a request-specific timeout, which is different than the connect timeout. This is specific to just this request. An example of what this may look like: again, you use the new builder factory to return you a new builder instance. In this case, the URI is being set to openjdk.java.net. A per request timeout of 1 minute is set. And this is going to be a post request. So the content type header is set. And in this post, we're going to post some JSON. We'll take a look at body publishers in just a moment, but it's sufficient to say that the JSON will be published as the request body. And again, once a HTTP request is built, it's immutable and it can be sent multiple times. There's no builder for HTTP response. Instead, you get a response as a result of sending a request. And again, you have the expected state, like the status code, the headers, if there are any, and or a body. You can actually get access to the actual version of HTTP that was used on the wire, because of course, that's negotiated with the server when you send a request. And you can get access to the request that corresponds to this response. Both asynchronous and synchronous modes of operation are supported. The synchronous API, it blocks the thread, as you would expect, until the HTTP response is available. The asynchronous API completes immediately, and it returns a completable feature of HTTP response. Completable feature was added in Java 8, and it supports composable asynchronous programming, and allows chaining of dependent actions that can be run either synchronously or asynchronously. This is an example of a synchronous send. So here, the client's send method is being invoked, and the request has been sent. And the body handler here, which we'll look at in more detail in just a moment, it's responsible for accumulating the response body bytes, and in this case, it converts them into a string. And in this example, we're just printing out the response status code and body. Similar example, but this time using the asynchronous mode. So rather than the send method, we use the send async method. It's given the same arguments, the request and a body handler, to determine how to handle the response body bytes. Here we're using the completable feature then apply method, and are effectively just peeking at the response because we want similar code that was in the previous example. So we just print out the status code. The second then apply method maps the HTTP response to its body type, which in our case is a string. And then finally, the then accept method consumes that string and just prints it out. So as I said, completable future was added in Java 8, and it's the Java platform's way of supporting composable asynchronous programming. Both request and response bodies are exposed in the API as reactive streams. Reactive streams are asynchronous streams of data with non-blocking back pressure. And we'll look at what that means in just a moment. And the HTTP client is effectively a subscriber of request body. So your application wants to publish some request body, and the HTTP client subscribes to that so it can be published. And then on the receiving side, the HTTP client is a publisher of response body bytes, and the application code can subscribe to that. So what are reactive streams? Again, you can have there can be whole conferences about reactive streams, and I just have a couple of slides. And it's important to explain this concept, the very lowest fundamental concept of reactive streams, because that's important to understanding how to implement body processors in the HTTP client. So reactive streams provide an alternative to the classic producer-consumer paradigm, where a producer generates items or data and puts them in a queue or buffer of sorts. And then at the same time, there's a consumer that consumes the data by removing them from the queue. So there's obvious problem here is how to make sure that the producer is not blocked when the buffer becomes full, or that the consumer is not trying to get data from the buffer when it's empty. And then you need some notification mechanism between the producer and consumer if this happens. And anytime you've got buffers in your code, you've got to worry about what size they should be and have to size them and memory usage. So reactive streams provides an alternative to this. In reactive streams, the producer on that side is known as a publisher, and the publisher publishes items. The consumer is known as a subscriber, and it receives items. The publisher has a single method subscribe that takes a subscriber, and the subscriber has 4 methods: on subscribe, on next, on error, and on complete. So a subscriber can be subscribed to a publisher by calling the publisher's subscribe method and passing the subscriber. The publisher then calls the subscriber's unsubscribe method with a subscription. It's this handshake between the subscriber and the publisher that results in the publisher having a reference to the subscriber and the subscriber having the publisher's subscription, and is given the subscription in unsubscribe. It's the subscription that acts as a mechanism for the subscriber to send signals to the publisher. For example, using the subscription, the subscriber can request a number of items from the publisher. The publisher can then publish at most that number of items to the subscriber by calling the subscriber's onNext method n number of times, each time with a single item. This request mechanism provides the subscriber with back pressure, since it is in control of the maximum number of items that may be sent to it. So we don't want the publisher going slower than necessary, and we don't want the subscriber to be waiting. If the publisher has no more items to publish, then it calls the subscriber's onComplete method. This informs the subscriber that the publisher, regardless of demand for more items, will publish no more items to this subscriber. If the publisher encounters an error, say reading from a file or a network, then it can inform the subscriber of this by calling the subscriber's onError method with a suitable throwable indicating the problem. So this is the basic low-level operation of reactive streams. And you can think of this as effectively 3 channels. There's a data channel through onNext, an error channel through onError, and a complete channel through onComplete. So in Java 9, the reactive streams interfaces were added to the Java util concurrent flow class. There's a publisher, a subscriber, a subscription, and then a processor. So as I said, the HTTP client is effectively a subscriber for request body, and the application publishes that request body to it. And then on the receiving side, the HTTP client publishes the response body bytes, and the application can subscribe to its publisher to receive it. There's also a notion of a body handler, and the body handler is an interface that allows inspection of the response code and headers before the actual response body bytes are received. And the body handler is responsible for creating the body subscriber. So digging into these interfaces just a little bit closer, the HTTP request body publisher is a flow publisher of byte buffers, and the byte buffers contain the request body data. The HTTP request body publisher, adds a single abstract method, content length. This can be useful to inform the HTTP client if the number of bytes being published is known in advance. So effectively, a body publisher is responsible for converting a higher level Java type into a flow of byte buffers suitable for sending as a request body. Now, we don't expect people to implement these interfaces themselves, at least not the average Java developer. Instead, these interfaces are being used and exposed in the API to provide an interoperability point with other Reactive Streams implementations. For most use cases, we provide body publishers in a body publishers class that consists solely of static factory methods that publish bodies of common types, like publishing the request body from a byte array or from a string, or streaming it from a file or an input stream, and a few other besides. Then on the receiving side, a body handler is a functional interface that has a single method apply that takes a response info, and this response info contains the status code and headers. The body handler is invoked when the status code and headers are available, but before the actual response body bytes have been received. And it's the job of the body handler to create the body subscriber, and the body subscriber is what's actually used to receive the actual response body bytes. So a body subscriber is just a flow subscriber of an aggregate of byte buffers. And the byte buffers contain the response body bytes. So body subscriber adds a single abstract method, getBody, that returns a completion stage that completes with a higher level type that the body subscriber implementation will convert the response body bytes into. So it's the inverse of the sending side. It's responsible for converting raw bytes into a higher level Java type. Again, we don't necessarily expect everyone to implement these interfaces themselves. So similarly, there's a body handlers and a body subscribers set of class that consists solely of factory methods. And they do similar things, like you can receive the response body as a byte array or a string, or stream it to a file, or make it available through an input stream. There are other handlers as well for discarding or buffering, and a few others besides. So moving on to some examples. Here is a simple example of how you may write a method that retrieves a given URI. A new HTTP client is created over which the request will be sent. A request is built with the given URI. Get is the default method, so there's no need to explicitly set it here. The client's send method is then called to send a request. The body handlers of string factory method will return a body handler that will convert the response body bytes into a string. So this send method blocks until the response is completely available, and then it returns the HTTP responsive string. And of course, in this example, we're just printing out the response body. Okay, so it's a similar example, but this time in the asynchronous style. Here we've changed the declaration of the get method. It now returns a completable feature of string, and that string is the response body. Rather than using the send method, we're using the send async method. It takes the same arguments as the send method. We're then using the completable feature, then apply, to map the HTTP response to its body type, which is a string. And that returns a completable feature of string. So there's no code here that blocks. Calling code may chain dependent actions on the completable feature that's returned by get, or it can just join it. Again, a similar example, but this time streaming to a file. We're using the body handlers of file factory to return a body handler that will stream the response body to a file. In this case, the The completable future will not return with the path until the complete response body has been streamed to the file. So calling code can be sure that when the completable future completes, that that whole response body has been written to the file. Again, dependent actions can be chained off this completable future, or it can just be joined. Here is an example of how you may do a GET request when you expect the response to contain some JSON. The JSON body as map method creates an unchecked object mapper. Well, of course, we know checked exceptions are problematic when used in stream pipelines. So here we're just creating an unchecked object mapper, which extends the Jackson object mapper and provides a read value that doesn't throw any checked exceptions. Instead, if an error happens, it will throw a completion exception that's suitable to pass through our completable future pipeline. Here is an example of a post request. This time, the request is being built with a body publisher of string that's capable of publishing the given data. In this case, we were doing a blocking send, and we're discarding any response body. We're not interested in it. All we care about here is the response status code, and that's why it's a HTTP response of question mark. And the response code then is just printed out. It's an example of a post request. Again, we're using the Jackson object mapper to convert the given JSON, which is a simple map of string to string, into flatten it into a string. Then we create a new HTTP request. We set the content type because it's got some request body. We call the post method, which sets the HTTP post method on this request. And we provide a body publisher that's capable of publishing this request body string. And then the client sends the request asynchronously, treats the response body as a string, maps it to its status code, and the status code is printed out. Again, callers of this post.json method need to either chain dependent actions that complete when the JSON exchange has happened, or else they can just join it. This is our last example, and it's a more advanced example, and it demonstrates how you can combine Java streams and completable future to send a number of requests and collect their responses. So the getURIs method here takes a list of URIs that we want to retrieve. The list of URIs is then converted into a list of HTTP requests by streaming over that and mapping each entry to a request builder and subsequently building a request from that builder and collecting into a new list. Next, each request is sent asynchronously, and the completable future of HTTP response are collected into a new list, and it's that list that gets returned. So callers of the getURI method can inspect the elements of the returned list to either chain dependent actions or query for their completion. So we don't have that many lines of code, and it can be quite powerful to write code like this. Okay, so moving on, I would like to switch over to the IDE, and we're going to write a custom body subscriber, just to show you that it's not that hard. And we're going to take a look at the interoperability with other Reactive Streams implementation and the API points for doing that. Okay, so here we have a simple get method. It retrieves a given URI and it returns the response body as a string. And we've seen this in examples. It creates a new HTTP client over which the request will be sent. Creates a new creates a new request to be sent, and then calls the send async method. Treats the response body as a string. Calls the completable future then apply to map the response to its body type and returns a completable future of string. Now, because I'm not brave enough to depend on the internet in a demo, I start a little server that's running on the loopback address, and this is just using the ComSolNet HTTP server that ships in the JDK. So it's going to return a response code of 200, and it's just going to have a response body that says, hello, JPoint. So this is not interesting. Let's move that out of the way. So our main method here starts the server. We call the get method with a given URI that's running on this machine, and we just join the completable feature that's returned. And then the response body is printed out. Let's just run that to make sure it's working before we make any changes. I'm using JDK 12 here, and as you all know, JDK 12, or Java 12 as well, shipped in March, just a couple of weeks ago. So response body says, hello JPoint. Very good. So let's print out the status code. It can be useful to see the status code as well. If you're doing this at home, you need to check that the result is not null, but because this is a demo, I'm pretty sure that there's going to be no errors, hopefully. All right, so we want to write a custom body handler, or body subscriber, that can replace the built-in handler that we're using here from the factory. So let's do that. So we need to implement the HTTP's body subscriber. I apologize, my typing skills don't improve when I talk and type at the same time. And it's a body subscriber of string. Okay. So we need to implement all of the flow subscriber methods, the on methods we talked about earlier. We also need to implement the HTTP's getBody method. So let's go ahead and do that. So the getBody method needs to return a completion stage. And we know that completable future is a concrete implementation of a completable stage, completion stage. So let's just go ahead and create an instance of one of them. It's a completable future of string. We'll call it a body CF. Okay, so we can just return that now. I apologize, I'll move that up. As we know, the onSubscribe method will be called when the subscriber is subscribed to the publisher. So we need to store the subscription that we're given. Oops. It's a flow subscription. And we'll just store that in the field. And as we know, with reactive streams, nothing happens unless there's demand. So let's issue some demand. We'll request just a single callback. So this subscriber is going to work in lockstep with the publisher. Every time it gets a callback, it's going to request another callback. For error handling, we will just complete the body CF exceptionally if an error happens with the throwable that we're given. So this, again, is not the most efficient implementation, but it's good enough for demonstration purposes. So every time we get a callback in onNext, we're just going to store the byte buffers into a list. We'll call that response data. So every time we get a non-next callback, we'll add the items to our list. This is actually buffers. Let's give that a better name. Okay, so we've hooked up everything apart from onComplete. And onComplete is where the magic happens. Again, this is not going to be the most efficient implementation. So what we'll do is we'll just determine the number of bytes we need, and then we'll retrieve all the bytes from our byte buffers, stuff them into a byte array, and transform that into a string. So the first thing we need to determine is the size of the byte array that we need. So let's stream over the response data. We'll map that to what's remaining in the buffers. Oh, and then we'll just sum it up. Okay, now we can create a byte array of that size. Just call it bytes. Okay, now we can loop over our buffers. Each time we go through the loop, we want to extract the data from our byte buffers. And we want to put it into the byte array. So buffer.get, we're going to put it into our byte array. At this point, we need an offset. So let's create one. And then we need a length. Oh. And the length is just what's remaining in the buffer. Okay. Each time around the loop, we're going to want to increment our offset, of course. So let's do that. All right, so now we've got all of our data into a byte array. Not magic, but there's more efficient ways to do this. Let's just convert that to a string. Again, for simplicity purposes, I'm going to completely ignore char set conversion, but don't do this in your own code. Oops. Okay, now we have converted our sequence of byte buffers into a string. We can complete the body CF with that string. Complete. Okay, so that wasn't too hard. We've implemented a custom body subscriber that offers similar functionality than the body handlers of string. Let's plug that in and use it. Ah, okay. Good catch. Let's try it without that and see what happens. Okay. New string subscriber. Oh, and because the client needs a body handler, which is a functional interface, let's give it that. Okay, let's run it and see what happens. Okay, well, that shouldn't have happened. Let's see why that happened. Sorry, could you repeat? Ah, short string. Okay, I'm missing something. Good, thank you. So let's put a repeat in here. Okay, now we'll see what happens. Let's see. Yeah, hanging, good. Let's get rid of that. Let's put in request 1. That's what you wanted? Okay. Oh, stop. Let's run it again. Okay, great. We have our status code, and we have many, many hello JPoints. Okay, good. So that's how to implement a body subscriber. What if you just have a flow subscriber? Okay. And that's a flow subscriber of a list of byte buffers. Okay, well, the flow subscriber knows nothing of the HTTP's getBody method, so let's get rid of that. And we don't need the body CF field anymore. For simplicity, we're just going to print out the error if one were to occur. Okay, we can get rid of that. But of course, this is a flow subscriber. And if the flow subscriber needs to make its data available somehow, it could write it to a database, or it could write it to a file or something else. In this case, we're just going to store the value into a field and make it available through an accessor method. So let's add an accessor. Get body, and it just returns the body field. Okay, so on complete now, rather than completing the body CF, it's just going to set this field. Okay, so now we just have a regular flow subscriber. How would we use that with the HTTP client? Well, the HTTP client provides a couple of API points for interoperability with existing flow subscribers, and let's use one of them. So we look in the body subscribers class. Well, we need a body subscriber string, right? And we look in the body subscribers class, and we'll see there's a number of from methods. And these from methods provide interoperability with existing flow subscribers. So let's use one of those. The first one, because we want to use a finisher function. We'll have a look at that now. So we use our flow subscriber, which is a string subscriber. And to complete the HTTP's completable future, we need a finisher function that provides the string value. So that's our accessor in this case, which is the getBody method. Okay, so now we have a body subscriber. Let's use that in here. We'll run that again to make sure it's working. Okay, it does. Very good. We'll make one more simplification in just a moment. So we can see here we've got a lambda, and it's unconditionally just returning the body subscriber. Well, the body handlers provides similar functionality, so we can just create the body handler directly. And that's a body handler. Okay, so now we have a body handler. We can use that directly as opposed to the lambda. And we'll just run that again quickly to make sure it's working. Okay, very good. So going back to the slides. Okay, let's move forward. Okay. So there are a number of adapter methods that support interoperation between regular flow types, like the flow publisher and flow subscriber, and their HTTP equivalents. So we've just seen some of these being used in the demo, the from subscriber method that has two variants. The first just accepts a flow subscriber and returns a body subscriber a void. And in that case, the flow subscriber must be making its data available through some external mechanism, like through a file or through an entry in a database. And we've seen in the example, we use the second variant with the finisher function to complete the HTTP's completable feature. Additionally, there are API points for interoperation with flow subscribers of string, where we stream the response body as a sequence of strings. And that's analogous to the buffered reader read line or the NIO files line methods that return a stream of lines from a file. On the sending side, there are adapters between flow publisher and the HTTP's body publisher. And additionally, there's a body subscribers of publisher method. And this guy is useful and came up very late in the development process. I believe it's useful in most cases for Oryx Java, where they provide pipelines of publisher subscribers, not through a chain of pub subs, but more by wrapping publishers to do the transformation. Okay, to sum up. The HTTP client is a replacement for the now legacy URL connection API that's been around for more than 20 years. We incubated it in JDK 9, we refreshed it in JDK 10, and we standardized it in Java 11. Code using the incubating version will need to be updated a little for Java 11. Minimally, the import statements will need to be updated to reflect the new package name. The API is small and compact. It uses modern language features like generics and Lambda, and it uses more modern APIs like completable future and the Reactive Streams interfaces. We learned how the HTTP client uses Reactive Streams, and we've seen the API points that exist for interoperation with existing Reactive Streams implementations. Because I work for Oracle, here are a couple of links where you can download the JDK. There are many places you can download the JDK today. These are just two of them. If you're interested in any of the work we're doing, please come and join us at OpenJDK. We're always looking for people to help out. Or you can follow us on Twitter at these hashtags or various handles. It's just some references as we went through. So that's all I have. So I think we'd have time for questions.
Yes. Yes, we have time for questions.
Okay, so there's a hand there, but just to say, there's a discussion zone afterwards, so please come and see me. One of the things I find very valuable about conferences is the social interaction. So meeting people, having good conversations and interesting conversations is a very important aspect. So please come and to the discussion zone afterwards, or if you see us in the social event, it always helps to have a beer when we're discussing such issues.
Thank you.
Thanks for the talk. Is there a way to configure pool size for connection pool, for TCP connection pool in client?
I understand the question. So the question is there a configuration to size the connection pool that's used by the client?
Yeah.
So we've been developing, the simple answer is no, not yet, at least. We've been developing this client for a long time. When we're trying to get something into the Java SE platform, we can't rush it. So the development process, as you go through it, you add all the bells and whistles to the API, and eventually you realize that you end up with something so complicated, it's very hard for people to use. So what we did then is we went through a number of rounds of simplification. So some of the things, like additional configuration for low-level things like connection pool sizes and things like that, we didn't expose yet in the API.
Is it planned?
Possibly, maybe, at some point. The more requests we have and the more data points we have, they will justify some of the work we do. So if many, many people want connection pool sizing, it's more likely to find its way into the API in the future. But we're definitely considering adding some API points. Connection pool sizing is a useful one, but in many cases, it's very hard for people to understand and to realize or to know what value to set.
So what is the default size of a connection pool in current implementation?
Oh, I can't remember off the top of my head. So there are some system properties available for configuring connection pool size, but they are not part of the API. Use them at your own risk. Of course, HTTP2 has a single connection between client and server. So if you're using HTTP2, of course, that connection will get reused. If you're not using HTTP2 and you're using HTTP 1.1, the client will reuse connections and will pool them. Off the top of my head, I can't remember the connection pool size, but what I will do is I will go and look it up and I will tweet it sometime after the conference.
Thanks. Is there anything for monitoring or something like that? Some maintains of maybe a mixed bin?
Do you mind repeating the question?
Is there anything to monitor the states of HTTP clients like MXBin or something?
No, but one of the engineers, Daniel Fuchs, who worked on the client, is also has a deep history in JMX, and he, as a personal hobby project, is looking into the possibility of adding such a thing. But right now, as today, there isn't.
Thanks.
Thank you for the talk. Did you compare it with technology, with others binary-based technologies like Google Protobuf or others? How much is more or less efficient with realization?
So I find that a confusing question, but maybe it's just me. You mentioned serialization framework like Protobuf.
Yes. In this technology, using byte serialization, no, classic thing, but how much is...
So, okay, I think I understand the question. So the question is, okay, I don't know how to frame the question, so maybe I'll just provide the answer. The body processors are not serializers. They convert the higher level Java type to a stream of bytes suitable for sending on the wire and then reconstituting. But they're not serializing the internal form of a string. They're not serializing anything. They're not serializers in the traditional sense of Java I/O serialization.